Hello, welcome back. Today we're going to talk about data vectors. So we'll start with this high dimensional data vectors and their use in data science. So in data science, the big idea is that we have observations and we have features. Observations are the rows of a matrix and the features are the columns of a matrix. For example, you might say this is an observation on housing data where certain features of the house, like the number of rooms, number of bedrooms, number of bathrooms, square footage, can all be variables, and they can be represented as a vector in a data set. So here's a great story. When Google went online in the late 1990s, one thing that set it apart from the other search engine was that its search results listings were always seems to deliver the good stuff up front. With other search engines, you often had to wade through screen after screen of links to web pages that just happened to match the search text. Part of the magic behind Google is its PageRank algorithm, which rates the importance of each page on the web, allowing Google to rank the pages and present to the user the more important and typically most relevant and helpful pages first. Now, this is all done with vectors and matrices. What about hardware? We cannot use the standard CPUs to process matrices in data science, so we need special hardware that can process whole vectors instead of one element at a time. This is where the TPUs come in. A tensor processing unit is a specialized hardware accelerator designed by Google to speed up machine learning tasks, particularly for neural networks. Now, TPUs are optimized for high performance computation with TensorFlow, focusing on deep learning workloads like training and inference. They're very good at handling matrix operations, which are the core of machine learning algorithms. Now, in general, data vector is an ordered collection of data elements, typically numeric or categorical, representing values in one or multiple dimensions. A vector is defined by both its magnitude and direction, making it a fundamental concept in fields like data science. For example, if an observation is represented by a data vector, then its direction and size compared to another vector can tell us a lot about those two vectors. So we will consider four types of vectors: numeric, categorical, logical, and data time vectors. Each one has many applications as shown. And for example, we can fit a model to a set of numerical observations or group data vectors that contain categorical values. We can also use logical vectors to filter data, and time series data is so important in many applications, including financial applications. So now, in terms of representing vectors or implementing them, we can use NumPy, a C-like library, to represent vectors more efficiently. Then we can apply various operations to manipulate them. So there are standard mathematical operations on vectors and matrices. For example, if two images are represented by matrices, adding their entries create an image, a new image that overlays one image over the other. So another important operation with vectors is the dot product that is simply obtained by multiplying corresponding entries of the vectors. There are many applications of dot product, including finding the cosine angle between two vectors that can tell how close the two vectors are. Now, vectors are fundamental in data science as they serve as tools for representing observations such as rows of data features and are essential for feature representation in machine learning. They enable mathematical operations that form the basis of many algorithms, from linear regression to deep learning. Vectors are widely used in tasks such as input features and prediction models, data aggregation and manipulation, Now, vectors make them important tool for data analysis and computational workflow. The ability to represent data and facilitate complex calculations underpins the many advancements in modern data science. So let's take a look at an example of implementation or use of data and thinking of an image as a data vector. So here's an image of me read into a Jupyter notebook, and I can look at the type of the image, and I can print the size of the image or dimensions, which tells me that this is 300 in height, 200 in width, and the third dimension here is the RGB values, red, green, and blue. So for example, if you print a one pixel contains, this is the red value, green, and the blue. So it does seem like that blue pixel is somewhere here that has a value of 213. The red and green are missing, so you can see much of this area, the pixels in this areas will be represented by a dominant blue value. Now, image can also be represented as a matrix of pixels, as we saw. Here's the Lincoln image, where each pixel can have 3 components representing RGB colors. And there are each color is represented by 1 byte or 8 bits. So you have 24-bit color, which is like 4 million colors that can be represented. And the transpose of a matrix M, for example, if you take a row of an image and then make it a column, so you actually rotate the image counterclockwise 90 degrees. So it's a very simple operation. Your ij element in the matrix becomes the ji element of the transpose. Now here's an example of how I have transferred myself. So for example, here I create a new matrix here, which is a bunch of zeros, and then I get the original matrix, the ji element becomes the ij element of the new matrix. So the B is the transpose of A. When I plot B, my image is rotated 90 degrees counterclockwise. We can also use vectors to do addition and transposition. So for example, I could take Lincoln's picture and transpose it and overlay on the top of each other. This might give you some interesting way to think about this. If you think of each image, that's a bunch of pixels. So here, if you form an expression like alpha times A, 1 minus alpha times B, if alpha equals 0, then what you get is the B. If alpha equals 1, you get A. And therefore, if you say this image is A, so that means this image is obtained when the alpha is 1, this image is obtained when if this is B, then this image is obtained when alpha is 0. And this is kind of in between. So if alpha is 0.5, I'm going to take 0.5 value from each pixel in the image A and 0.5 value for each pixel in the image B. I create that overlay, impression of overlay. So this is using first principles to manipulate images or vectors. Now, sentences, you can think of a sentence in a document as a vector in n dimension. For example, if you have the center, I love machine learning, that can be represented by 1 in all of these things, but it doesn't have coding or other things. If you take the document 2, it says machine learning is great. Document 3 is I love machine learning, coding, and that's where we end. So you have these documents as vectors, and we can ask questions like, how close are these vectors? What's the angle between document 1 and document 2, and document 2 and document 3? Those things can tell you maybe how close they are in terms of their word composition. The cosine angle between two vectors is given, which is very important to find the angle between two vectors, the angle between two documents, is given by the dot product of AB divided by the size of A, size of B. So this size of A is the length of A, the Euclidean length, B is the length of B. we can ask questions like, what if the cosine angle between two vectors is 1? Then the two vectors, that means cosine of 90 is 1. So that means the two vectors are orthogonal direction. This means maybe if they are documents, then one document has nothing to do with the other one. If the cosine angle between two vectors is 0, which means they're kind of on each the same angle, so we know that the two vectors are in the same direction. We cannot say they are the same vector, but say in the same direction. So that means something there. Now here's an example of how to find the cosine angle. Let's say you want to find the cosine angle between 1, 2, 3 and 1, 2, 1. Here's the formula for finding it. We find the dot product by taking the product of these elements, the corresponding elements. We find the size of u, which is the square root of 1 squared plus 2 squared plus 3 squared. We find the size of v. We find the cosine angle between the things, and then we find the angle is 49.11. Now, this angle is an indication of how close the two vectors are. For example, if two documents are represented by vectors, then the angle between them indicates how close they are. So if the angle is smaller, that's better because they're close in some sense. If the angle is like 90 degrees, then they have nothing to do with each other. So you can also think about document as vectors. Here's another way to look at it. Let's say you consider 3 documents, I like apples and all that. So we have the word vocabulary, that means all the words in here. And then document 1 contains I like apples, document 2 contains I like oranges and apples, and document 3 contains apples are tasty. Now, if you actually take the dot product of these two vectors, you will see that the dot product of doc1 and doc2 is like, I think it's 3, and the dot product of doc1 and doc3 is 1. So you have to say doc1 is closer to doc2 than to doc3, which kind of makes sense. I like apples, I like oranges and apples, so there's I like apples, or in both cases. Now this one, the only thing common between doc1 and doc3 is apples. So you can see that doc1 and doc3 are not too close, but doc1 and doc2 are closer. And we can get that from the dot product. Now, so here is an example. Let's say that we read a CSV file and we get a bunch of data points, column 1, column 2, and column 3. Column 3 is numeric, column 2 is categorical. Now, one of the things we have to do is to convert categorical to numerical before you can compare anything. So we do that by doing one-hot encoding. So in one-hot encoding, if an observation has A in it, like first one and the last one, we have a 1 in this vector. If an observation has a B in it, we have 1 here. This one has C here, this one has D here. So in fact, depending on the number of categories, we have to create new columns, and now we have data vectors. Now, so how can we determine if the two rows are the same? We can certainly take the dot product of the row 1 and the final row, row 5. If you take the dot product, you'll see that they are the same. The angle between them would be 0. So you're going to get the angle between, which is like you're going to get the this dot product to be the angle between them to be 0, which means that the cosine angle would be 1. Now, so that's not an indication that they are the same, but they are really, you can inspect them and look at whether they are the same. Now, projecting data vectors from one dimension to another dimension is an important part of data science. So, for example, let's suppose we have data points in 3 dimensions. So you can imagine this cylinder having points on the surface. So you can see that, right? Now, if you think about this cylinder, these points can still be represented by a 2D vector without losing much of the information. So if you flatten this cylinder, you get the same point, that distribution, just like this. So here, what we did was we reduced the dimension of the data set from 3D to 2D. These are the points in 3D, now these are the points in 2D, and you need one less information to represent this, but the analysis can be the same. Now this is a big part of data science, projecting vectors from one dimension to another, which allows us to save space and make the processing more efficient. Now, one of the important problems with the data science is the sort of like least squares problem. It's a mathematical optimization problem that minimizes the sum of the square differences. So it's a great fit. Like, for example, if you've got a bunch of points, then you're going to try to find the best fit line or best fit curve, depending on how the points are distributed. You try to find the curve of the points that are closest. So when you have that, then if you have an observation that's not here, say 4.5, you can estimate the value of it based on that fit. So that's the least square model. So the least square model is to reduce the error between the predicted is the line, observed is the points, and there's a little gap here between those two when you make the prediction. So you want to try to minimize the sum of those errors. So that's why it's called the least square method. Now, here's, without proof, I'm going to give you an example of how to use least square method. Let's say you got 3 points, 1, 2, 2, 3, 3, 5. You're trying to find the best fit line to this. In other words, this red line, the equation of that. Now, that you can find the equation of the line by using y equals c0 plus c1x, and this is the one that minimizes the, so what slope, slope is the c1, y-intercept is c0, what of c1 and c0 values minimizes that, because you can find many of those things, but which one minimizes the least square error? Without going into details, so here's the coefficient c1 is given by this, c0 is given by this. So let's say we are given these points x, y, we're given these 3 points. We find the mean of x coordinates, 1 plus 2 plus 3 divided by 3, the mean of y coordinates. Then we find the xi minus x bar, yi minus y bar for each point. So each point we take x and subtract x bar from it. So 1 minus 2 would be minus 1, and so on. Same thing here. You take each point of y, subtract the mean, 2.3 for y, 2 minus 3.3 for y. So 2 minus 3.3 is 1 minus 1.3. So we do the same thing for all the points, and then we multiply these two to get 1.3, and then we take the square of this column, xi minus x bar squared, so that's minus 1 squared, 0 squared, and 1 squared. Then we find the sum, which is what it's given here. So the sum is going to be, so the C1 is given by this sum, which is 3, divided by the sum here, which is 2. So we get C1 to be 1.5. So C1 is the slope. And then C0 is the 3.3. C0 is given by y bar, which is 3.3, minus c1 times x, so it's 1.5 times 2, so which gives you 3.3. So that's the y-intercept. So you can see this line seems like the slope is 1.5 and the y-intercept is 0.3. And this looks like a good fit. I mean, this is the best fit, in fact, from a least square perspective. So this is the best model we can do. So that's an example. Now, another thing about the this word using vectors. There's a package called Word2Vec. It's a popular algorithm used in natural language processing. It's a great technique that transforms words into dense, fixed-length numerical vectors. They capture the semantic meaning and relationships. This is developed by Google researchers. It employs the neural networks to create word embeddings by training on large text corpora. The model, which predicts the target word based on its surrounding context, the resulting vectors are going to be positioned in a high-dimensional space such that the words with similar meanings or usage patterns appear close together. For that capability enables Word2Vec to capture analogies like king is a man and queen is a woman and things like that. So here's an example of this type of application where you can implement it using a Jupyter Notebook. So in conclusion, there are many challenges to working with vectors, and we'll talk more about the vector databases and other things as we go. Bye now.